Good morning, students. Welcome to today's class. Today, we are studying about Shannon's third law, that is also called the Shannon-Hartley law or capacity of a band-limited additive wide Gaussian noise. Okay, so this is Shannon's third law or Hartley law. So we have already studied Shannon's first law, second law, and this is also called Shannon's third law or Shannon's Hartley law. It deals with the capacity of a channel where the bandwidth is limited. So here we are considering only band limited channel, and the waveform received at the receiver may be accomplished by a waveform which varies with respect to time in an entirely unpredictable manner. This unpredictable signal is called noise. Okay. Also, we are considering a band limited channel, and the waveform at the receiver may, along with the input at the receiver side, we will get an unpredictable signal which is called noise. Okay. That is y is equal to s plus n. In most of the channel, this noise is white and is a Gaussian distribution. Hence, this noise is called additive white Gaussian noise. So, here we are saying for any system, when we are giving an input x to a system and we are getting output y, in the channel, a noise will be produced. So, this noise, in most of the cases, this noise it's a white noise and has a Gaussian distribution. So this noise is called additive white Gaussian noise. So Shannon's Hartley law states that the capacity of a band limited Gaussian channel with additive white Gaussian noise is given by C is equal to B log into 1 plus S by N bits per symbol. This is the equation for Shannon's Hartley theorem. Here B is the channel bandwidth in hertz and S is the signal power in watt and N is the noise power. Okay, now we can discuss the proof for this Shannon's Hartley theorem. Okay, this is the proof for Shannon-Hartley theorem. We have, according to Shannon-Hartley theorem, C is equal to B log 1 plus S by N bits per symbol. That is, C capacity is equal to B log into 1 plus S by N bits per symbol. This is Shannon-Hartley theorem. So, in this session, we are deriving the proof for Shannon-Hartley theorem. Okay. Now, we want to prove the capacity C. So, we are starting with the capacity C is equal to maximum of I of X semicolon Y. That is maximum of mutual information. Now, we have equation for mutual information as I of X y is equal to h of y minus h of y by x. This is the equation for mutual information. Okay. Now, we have the joint entropy at the channel. So, if this is a system, we are giving input x and we are getting output y. So, this is the channel. Here, in this channel, noise is adding in the channel. So, output y means if the noise is 0, then output y means what we are sending input, that is equal to output. So, what we are sending x, that is y is equal to x. If there is a noise, then the output y is equal to x plus n. This is a system. Okay. Now, the joint entropy at the channel. So, at the channel, the joint entropy means the input x and noise n. So here the joint entropy at the channel, we have h of joint entropy h of x comma n, which is equal to, we have joint entropy equation h of x plus h of n by x, because joint entropy at the channel means we are considering input and the noise at the channel. So, joint entropy h of x comma n is equal to h of x plus h of n by x. Okay. So, we can rewrite it as h of x comma n is equal to h of x plus h of n by x, means it's simply noise. So, we can write h of n by x as h of n. So, this is equation 1. Now, we want to derive at the receiver end the joint probability. Now, the receiver end, what is the joint probability? So, we are sending x input and we are receiving y as output. So, at the receiver end, we are considering only x and y. So, So the joint entropy at the receiver end is h of x comma y is equal to h of x plus h of y by x. So this is the joint entropy at the receiver end, and this is the joint entropy at the channel. So after that, this main equation, that is mutual information equation, can be written as equation A, and this joint entropy at the channel can be write as equation 1, and joint entropy at the receiver can be write as equation 2. Okay. Now the received signal Y is the combination of input signal X and noise N. Okay. Y is equal to X plus N. So for an invariant channel, the entropy can be written as h of x comma n is equal to h of x comma y. That is, Y is the combination of input and noise. So we can rewrite as the joint entropy at the channel is equal to joint entropy at the receiver. That is, h of x comma n is equal to h of x comma y, because y is the noisy version of x. So we can write the channel, the joint entropy of the channel is equal to joint entropy at the receiver. Okay. Now this is equation 1, that is h of x comma n, and this is equation 2, that is h of x comma y. Now we can equate these two equations, that is equation 1 and equation 2. So by equating, we get h of x plus h of n is equal to h of x plus h of y by x. That is, h of x plus h of n is equal to h of x plus h of y by x. Here h of x and h of x are common. So when we take it one side, we get it as 0. Now from this we get h of n is equal to h of y by x. So the conditional entropy of y with respect to x is nothing but h of n. So y is equal to x if n equal to 0. So for an invariant channel, h of n noise is equal to h of y by x. Okay. Now equation A, that is, this is equation A, mutual information, that is I of x comma y is equal to h of y minus h of y by x. So we can replace this y, h of y by x, as h of n in equation A. So the equation A become I of x y is equal to h of y minus, instead of h of y by x, we are writing h of n. That is h of y minus h of n. So put this equation as equation 3. Now we got the equation for mutual information. So we have the equation for capacity is equal to maximum of mutual information. So we can rewrite equation for capacity C is equal to, this is mutual information, h of y minus h of n maximum. So capacity C is equal to maximum of mutual information, that is h of y minus h of n. Okay. If the noise is additive white and it has a distribution of Gaussian distribution, and noise power with the n, the power of noise is the n, with a bandwidth b hertz, then the equation for entropy of the noise is equal to b log 2 pi E n beats per second. Here, this is the general equation for entropy of the noise, that is h of n is equal to, in terms of bandwidth and noise power, that is b log 2 pi E into n. Okay, bits per second. Given the input signal is limited to an average power S, then take the power of input signal X as S over the same bandwidth B, then the signal at the receiver. The signal at the receiver Y is equal to the input power S plus the noise power N. So Y is equal to signal power Y is equal to input noise power S plus, input signal power S plus noise power N. Okay, so Y is equal to S plus N. Now, by looking this equation, we can create equation for entropy of h of y, that the output at the receiver h of y max is equal to b log 2 pi E into y. In terms of n, it will become b log 2 pi E into y. In terms of y, we are writing S plus n. Then we get b log 2 pi E into y. In terms of y, we are writing S plus n. So entropy of h of y is equal to b log 2 pi E into S plus n bits per second. Now we have equation 4 that we have already generated. The capacity C is equal to h of y minus h of n max. Okay, so instead of this h of y, we are writing this equation h of y, and instead of this h of n, we are writing this equation for h of n. So by substituting these two equations, we get Cc equal to b log 2 pi e into s plus n minus b log 2 pi e into n. Okay, then we have log a minus b is equal to log a by b. So by writing like that, we have b log 2 pi e s plus n by 2 pi e n. Okay, by cancelling this 2 pi e in the denominator and numerator, we have b log s plus n by n. By dividing this n with the s and n, we get s by n plus n by n. That is 1 plus s by n. So C is equal to b log 1 plus s by n bits per second. This is the equation for capacity of a Shannon-Hartley theorem. So this is the proof of, this is how we are proving the capacity of a Shannon-Hartley theorem. So that's all about today's class. Thank you.